To find the threshold energy, we need to find the minimum value of the kinetic energy for this process. And if we start with the available energy equation, which says 2 times capital MC squared times E sub M plus MC squared. And because the final state includes the 2 original protons that have mass m and the pion which has mass m sub pi, the threshold energy that is corresponding to the minimum energy case, in which all of the particles are at rest in the center of momentum system. The total available energy A must be at least the total rest masses. And so we can say that E sub A has to equal 2 mc squared plus m pi c squared, 2 because we have 2 protons. And if we plug this into the equation above, we get something to the fact that 4 m squared c squared, c to the fourth, plus 4 m pi c to the fourth plus m pi squared c to the fourth has to equal 2m c squared em plus 2 mc squared quantity squared. And now we can say that em would equal mc squared plus m pi c squared times 2 plus m pi over 2m, and that is the same as mc squared plus k, which means that k equals m pi c squared times 2 plus m sub pi over 2m. And we see that the bombarding proton's kinetic energy k must be somewhat greater than twice the pion rest energy. So if we plug in some of these numbers, mc squared is 900, we're going to em now, is going to be 938 mega electron volt, plus m pi c squared is 135 mega electron volts, and m pi over 2m is 0.072, and we get k in this case to equal 135 mega electron volts times 2 plus 0.072, or 280 mega electron volts. I did not do the calculation for this, but we can find what the available energy is. We were not asked for it, so you don't have to find it. We just needed the K part